Yeah, thanks very much, Prim, and thanks, Katerina, also for organizing. So Maciek can't be here this week, but I guess just on behalf of the local participants, we're all very happy that you're here with us in Cambridge. So hopefully it'll be a good month. Yeah, so just before we start, most of this is based off of this article with Maciek, which is going to appear in Journal of LMS soon. And also, there's also some notes that are typed up if you're interested in reading those at all. So today I'm going to be talking about new constructions of complex hyperkähler metrics, and in particular in relation to joist structures. Now, the talk I think will be pretty concrete, but since this is the first talk on joist structures for the program, probably nice just to maybe explain some of the context as to why people are interested in joist structures. So joist structures are motivated by Donaldson-Thomas theory, and I can't say I'm a full expert on DT theory, so I'll sort of do my best to explain the story as to why people are interested in these metrics. There's probably also a parallel story you could tell from the physics point of view as well. So Donaldson-Thomas theory is the study of enumerative invariants of Calabi-Yau-3 categories. So these are categories that are meant to capture some of the geometry of a Calabi-Yau-3 manifold. So for example, the Fukaya category is meant to capture the symplectic geometry of a Calabi-Yau-3. And then one associates Donaldson-Thomas invariants to classes in the category. And these invariants, in a sense, count distinguished objects called stable objects in each class. So in the case of the Fukaya category, it's sort of conjectured that one can set DT theory up by saying that the stable objects are special Lagrangian submanifolds of a Calabi-Yau-3 manifold. Now, the notion of special Lagrangian requires a choice of complex structure and a holomorphic volume form on your Calabi-Yau-3, and that's some sort of data from outside the Fukaya category, which only sees the symplectic geometry of your manifold. And so the Donaldson-Thomas invariants can move, in fact, jump discontinuously as you move around, as you change the complex structure. So that motivates the study of a space, which I'll call M, of stability conditions on a Calabi-Yau-3 category. And Tom Bridgeland, sort of given some, relatively comprehensive technical assumptions on the category C, explains that because the Donaldson-Thomas invariants jump around in a controlled way as you change the stability condition, there should be a geometric structure called a joist structure on the space. Basically, the holomorphic tangent bundle of them, quotient by some integral lattice, which comes from the stability conditions. In a paper of Bridgeland and Ian Strawn, this is interpreted as a complex hyperkähler metric with a whole bunch of extra symmetries. Okay. Now, there are sort of, as far as I understand, there are very few concrete realizations of spaces of stability conditions. But in the case that the category is the Fukaya category of a particular Calabi-Yau manifold, these are Calabi-Yau manifolds which fiber over some Riemann surface of genus G. Yeah. Oh yeah, sorry, it's a bit. Yeah, it's a bit squeaky. So yeah, the Calabi-Yaus will fiber over a Riemann surface of genus G. And one can actually, in a very special way. And then there's some nice papers of Tom Bridgeland and Ivan Smith, which together basically realize this space of stability conditions as a space of quadratic differentials on a Riemann surface of genus G with simple zeros and a sort of prescribed set of poles of particular orders. So here the quadratic differential. So you can think of points in this space as being Riemann surfaces together with some section of basically the square of the canonical bundle with simple zeros and prescribed poles of these orders. And basically these pole orders describe how this vibration happens. And that sort of raises the question of can you see the joy structure from this side of the correspondence, while sort of forgetting about Donaldson Thomas theory completely, and not worrying about DT invariance. So can we sort of construct this arrow here? This arrow here is quite hard because it involves solving some Riemann-Hilbert problems based on the Donaldson Thomas invariance, which the solutions to which are not really understood in except for a few small cases. And so, yeah, you might think that it might be easier to see the complex hyperkähler metric from this side of the correspondence. So in the case of a Riemann surface and quadratic differentials with no poles, so holomorphic quadratic differentials, this construction has been carried out by Tom Bridgeland. And in the case of genus 0, so quadratic differentials on the Riemann surface, on the Riemann sphere, and a single pole of order 7, this has also been carried out by Bridgeland and Masuero. And so today we're going to be considering, so genus 0. So I'll just think about quadratic differentials on CP1. And we're just going to consider a single pole of odd order. So the minimal order of this pole being 7. And sort of that's sufficiently complicated that it maybe motivates one to come up with some general ways of calculating exactly what this hyperkähler metric is from this perspective. And sort of hopefully by the end of the talk, I'll basically just give you a formula for the hyperkähler metric. Yeah, so it's even though there's only one pole here, I think this sort of elucidates how one might proceed in the general case, at least when one is working in the genus 0 setting. And one has poles of odd orders. Even order poles are a little bit harder. So now I'll just sort of get much more concrete. So let's think about how one might find local coordinates on this space here. So I don't have to worry about the Riemann surface because I'm always dealing with CP1. But only care about quadratic differentials up to Mobius transform, which preserves the quadratic differential. So if I write a general quadratic differential in terms of a local parameter on CP1, it would just be equal to some rational function times by dx squared. And I want this thing to have a single pole. So I may as well act by Mobius transforms to sort of use up my gauge freedom to put these in some normal form. And in fact, I can always act by a Mobius transform so that the quadratic differential takes the following form. And basically, these A's now give local coordinates on my space of quadratic differentials because I've used up my freedom to act by Mobius transforms up to some finite rescaling of X by a root of unity. So these A's really do give local coordinates on this space, which is actually a manifold. And you can see this quadratic differential will have a single pole of order 2n plus 5, just because dx squared will have a pole of order 4 at infinity, right? Okay, so now I want to talk about complex hypercalorimetrics, and sort of this may be a story that's familiar to you, and you may find this not that complicated, but I think it's important, and maybe it is new to you, in which case I should definitely say it. So I'm going to be talking about complex hypercalorimetrics. So here, X will be a complex four manifold. And we're going to be considering, well, metrics G, which I guess are sections of the metric power of the cotangent bundle. But here I really mean the holomorphic cotangent bundle, right? So for these metrics, there's no notion of signature or anything. So this differs slightly from, Riemannian geometry. And to have a hyperkähler structure, I need three holomorphic endomorphisms, I, J, K. Which satisfy the following conditions. So, well, I need them to satisfy the quaternion algebra. I need them to be, I need this metric to be Hermitian for these complex structures. And also I need them all to be parallel for the Levi-Civita connection, right? To have a hyperkähler metric. Okay, so it's basically the definition you expect, except we have a holomorphic metric instead of a Riemannian metric. So on our way to constructing complex hyperkähler metrics, we're going to encounter some intermediate data, which we're going to build the hyperkähler metric from. And it's the following thing. So we'll have our complex manifold X, this CP1 lying around. And I'll use coordinates U0 and U1 for kind of homogeneous coordinates on CP1 like so. And then I'll do something that may look a little bit silly, which I'll call H bar to be the coordinate on CP1. So luckily there, yeah. I don't know, maybe you find this a little bit strange to use H bar as the coordinate on CP1. Hopefully by the end of the talk, it may not look quite so crazy. So we're going to be looking at Twistor distributions, basically. So we'll have some L, I'll call this space here F, actually. We'll have some subbundle of the tangent bundle of F. And these will be rank 2 distributions of the following form. So use J, actually. So these are rank 2 distributions. And what I'll require is I'll require these U's and these V's to give a trivialization for the tangent bundle of X together. So yeah, so these U's and these V's together trivialize X, trivialize the tangent bundle of X. And we're always going to assume that L is integrable, in which case we can talk about the Twistor space. So maybe shrinking X to avoid some Hausdorff issues, we can talk about Z, the quotient of F by L, okay? And so in our case, there's a natural fibration of Z over CP1. The fibers are just labeled by this H bar coordinate, okay?
What's M?
Sorry?
What is M? Because you say that X is 4.
What is the space of quadratic differentials? That will appear later.
Oh, yeah.
Yeah, okay. So basically X will turn out basically to be the tangent bundle of the space of quadratic differentials. Thanks. So we can talk about the Twistor space. So I'll just write here integrable, so that to remind us that we're in the integrable setting. And in fact, we can define a quaternionic structure just the following way. So if I let J act that way, and K. Act that way, and then I enforce the quaternion relations, then I get a quaternionic structure. And even though I'm sort of writing it in terms of this basis I've chosen for L, this is actually really associated to the distribution L rather than any choice of basis. And there's also some distinguished family of metrics on X associated to this distribution. So I call these the compatible metrics. So these are metrics of the following form. I just take any sort of non-degenerate skew matrix of holomorphic functions. And then I write down one of these things where the U's and the V's are the dual basis for the trivialization of Tx. And basically, each of these metrics is automatically Hermitian for the complex structures. So it's local, so no. What do you mean by simple?
It's local.
Yeah. Everything will be local in the stocks. Yeah, thanks. Okay. So I'll briefly, many of us in this room like parabolic geometries, so I'll just explain what this, or give this a name as a parabolic geometry. So, there's various names, but probably these appear earliest as 2n2 paraconformal structures. These are examples of paraconformal structures. And these are explained in the paper Bailey and Eastwood in 1991. And then also kind of more recent literature would use maybe the term 2n2 Grassmannian. Structures. And sort of the standard reference for parabolic geometries has a nice exposition on these things. So that's in Chaplin-Slovak book. And I guess the name paraconformal structure comes from the fact that you can talk about alpha planes and beta planes in the same way as in sort of regular conformal geometry. And indeed, if n equals, sorry, this should be X should be a 4n fold here. That's a bit confusing. Right, sure. Yeah, thanks, Ross.
So here for geometry.
So it's something like SL2 cross SL2 in the conformal case, right? So it's a reduction. Where this is rank 2, and this is rank 2n. That's this G structure. Yeah, so I guess the name Grassmannian comes from this is like, locally modeled on or some curved analog of what happens on, it's the Grassmannian of 2 planes in C2n plus 2, right? So this is the flat model of the parabolic geometry. Okay, but yeah, I won't talk too much more about parabolic geometry. So we have this family of compatible metrics. And one of the questions obviously you want to ask is, when will this family have a hyperkähler representative? And it's a bit like asking for a Ricci flat scale in a conformal class. So what we're going to do is we're going to encode the hyperkähler condition for this metric G in terms of some data on the twistor space. Okay. Okay, so what I'm going to do is I'm going to take my metric and then just write down a 2 form on F. And I'll explain what this 2 form is in a second. So I take my E here, and then I write down the following thing. And so what sort of two form is this? Well, as the two form on F, I can think of this as a relative two form because I mean, it's just a product and there's no DH bar terms. So this is a relative two form. Just, I guess in this context, just means no DH bar terms. If I sub my H bar back into this two form, then what I get is I get a homogeneous polynomial on C2, right? And so this is actually an O2 valued relative two form. So in this trivialization, there's this pole, but really we should think about this as an O2 valued thing. And it's also set up so that the kernel of this thing is precisely L, okay? So, sorry. Kernel of omega is equal to L. And so if I expand omega out, I'm going to need to do this. So what I'll do is I'll call this front bit here omega minus, and that there omega plus. And now let's just assume that omega is relatively closed, so differentiating in the x directions. So dx omega equals 0. It's easy to see that it implies that omega minus and omega plus are closed as two forms on x. But basically, omega plus is actually g j dot minus I plus I g k dot. And so these being closed are actually equivalent to the Kähler forms being closed. So I've just taken a metric which corresponds to some skew matrix, non-degenerate skew matrix of holomorphic functions on my X. Yeah, at the moment it's general, but I'm now enforcing this closure. And yeah, it's all very sort of concrete, but when you're in the case we're going to consider, we sort of get the data in a very concrete fashion. So that's why I'm being concrete. So yeah, this implies that sort of d omega I, d omega j, and d omega k are closed, which is equivalent to the closure because the integrability of this is actually equivalent to the integrability of the plus or minus lowercase I eigenspaces of the complex structures. And so dx closure of omega is actually corresponds to G being CHK, so complex hyperkähler.
What happens to EIJ coefficient in the middle?
I've just forgotten to write it. Thanks. Yeah, there we are. And so what I'll do is I'll call one of these things, a two form satisfying these things, while also being, I'll call a two form satisfying these things, a two form satisfying dagger. And then basically there's a correspondence between, so G is the correspondence between two forms satisfying dagger and also dx closure and complex hyperkähler metrics of in this family. Non-degeneracy. Yes, that's this kernel of omega is equal to L. So it's maximal rank well and L. And so indeed in this case, then we have the following thing, because the Lie derivative in the direction of omega, sorry, in the direction of these, in the direction of the Twistor distribution of omega is equal to 0. And so omega descends to the Twistor space. So this is a correspondence between certain two forms on Twistor space and complex hyperkähler metrics in this family. Okay, and so basically, we're now going to completely change tack, but the thing to keep in mind is we're looking for these kind of two forms. So I might give these a name. I'll call these CHK2 forms. So two forms satisfying this while also being dx closed. All right, so that's sort of the general introduction to complex hyperkähler metrics and their twistorial interpretation, at least locally. So now we're going to talk about families of ODEs. So we'll have our X and our CP1 with coordinate H bar. And I'll give X local coordinates A, which will be in C2n, Q, which will be in Cn, and R, which will be in Cn. And points in X cross CP1 will correspond to ODE of the following form. There may be Schrödinger equations, where this potential is going to be, well, I'm just going to write the potential out, and it will sort of seem to come out of thin air. And hopefully I can try to explain it later in a second. So the potential Q of X will basically be expanded to three orders, three orders in H bar with no further terms. So there'll be a Q0 term. There'll be a H bar to the 1 term. And there'll be a H bar squared term. And then we're just going to stop. The Q0 will just be the quadratic differential. So it's labeled by these A's. So this setup is really due to Tom Bridgeland. It was the natural generalization of what Tom Bridgeland did in higher definitions, higher dimensions. Yeah, let's say that the ODE has dependent variable psi. X, sorry. Yep, I'll write that in full then. So D, so. Yep, that's maybe more clear. And then Q1. So Q0 will just depend on our A coordinates, and that corresponds to the quadratic differential. And the Q and the R are, well, we can kind of think of these as somehow fiber coordinates, because it's a natural fibration of this space X over the space of quadratic differentials. So this is a sum of simple poles plus also some polynomial term. Where here these PIs are defined by the following equation. So there's some sign ambiguity in the PIs. These are only local coordinates. And so earlier I said that the joist structure should exist on the space Tm mod some lattice. And I probably don't have time to explain today, but maybe you can ask me about this after, is that once you've picked your quadratic differential, there's a map that basically goes from the space that parameterizes the Q1s, so these Qs and the Rs, to the tangent bundle mod some lattice, some canonical lattice. So this is a little bit like the Arbel map. We can write it in terms of the Arbel map. It's not quite the same because the ranks of the torus bundles are different, but yeah. So the complex hypercalorimetric we'll see easily on X, and then there's some procedure to transfer this over to this space here, which is really where the joist structure should live. But sort of today I'm just going to focus on X because everything is very nice there. And so once we've specified Q0 and Q1, Q2 is uniquely specified. So Q2 of X is determined by, we need the following Laurent expansion of Q of X at each of these simple poles. Where UI is just some holomorphic function on X. And this looks like quite an arbitrary condition. It has a very natural interpretation in terms of solutions of this ODE. So here X is a complex parameter, and we're looking for sort of analytic solutions. And if I take a local solution and I analytically continue that solution around this pole, basically the solution will be multiplied by -1, right? Because there's some monodromy around this pole. So Q2 is just the unique meromorphic function which satisfies this condition. And yeah, there is a formula for it, but sort of not much point in running it out. Yeah, so yeah, maybe it still looks a bit plucked out of thin air, but at least Q0 and Q1 have real geometric interpretations in terms of the space of quadratic differentials. Okay, so now we want a Twistor distribution on the space on this space. And so the way we're going to do that is we're going to try to deform this equation while preserving something called Stokes data. Okay, so the procedure goes as follows. Around this ODE has a big irregular singularity at x equals infinity. So one goes to the complex plane at x equals infinity, and because of this exponent here, one can canonically cut up the complex plane into some overlapping sectors. And there's something called the Stokes phenomenon, which says that there's a unique solution of this equation with some prescribed asymptotic behavior in each sector. And so thinking about this equation as a 2x2 system, there'll be some matrices which relate the solution in each sector. This is called the Stokes phenomenon. And what we're going to do is we're just going to ask for, well, basically paths in this space which preserve the Stokes data, so preserve the monodromy data. And yeah, the fact that, well, basically paths in this space which preserve the Stokes data, so preserve the monodromy data. And yeah, the fact that there is some Stokes data which is being preserved is not really going to be important for seeing the complex hyperkähler metric, but that's the interpretation of how we're actually going to construct it. So we're going to just use the general theory of isomonodromic deformations without much comment. So this theorem is due to Jimbo, Miwa, and Ueno. And it says the following thing. So if I have some path in my space of ODE, this path will be preserving the Stokes data. If and only if the following equation is satisfied. So we have some potential, and we're differentiating it with respect to our time parameter as we're moving around the space X. Where here A is just some undetermined meromorphic function. Okay, so in our case, we probably want to think about like a distribution spanned by these flows. So maybe I'll instead write this theorem in terms of the generators of these deformations. So some vector field will generate a deformation which preserves the monodromy if and only if I take the potential, I differentiate it in the direction of the vector field W, then we get this thing on the right-hand side for some meromorphic function. And so this, if we think about this for a second, W here is some vector field on the space of AQ. Okay, so now I'll state a theorem. Which is that there are two n-linearly independent W satisfying this equation. That's span and twisted distribution. Yeah, that's right. And so as you vary h bar, you get a twisted distribution. Okay. And so, well, the proof is not really a proof as much as a direct calculation. You just sort of plug Q into here, and then you later on expand everything at various poles, and eventually it's determined exactly what these flows are. And yeah, a bit time consuming, but it's not that difficult. And furthermore, we find what A's are. The A's are just some sum of simple poles at these points Qi indexed by this Q. And so we have this twisted distribution, and now we want to know, well, is there a complex hyperkähler metric on X? And yeah, the way we're going to do that is we're going to try and find a CHK2 form. So associated to this ODE what I'm going to do is I'm just going to take the potential and I'm going to ask you to consider the curve. So let's take a generic P in X and some generic H bar. And then I'm going to consider the curve sigma, which is basically the Riemann surface or algebraic curve defined by this equation. And so generically, this is a non-degenerate thing because this Q will have simple zeros. And yeah, I need to compactify with some point at infinity the usual way. But this curve comes equipped with a canonical meromorphic one form. And it's the meromorphic one form I'm going to call phi. And it's just equal to, well, it's basically the square root of the potential, if you like. It's just y dx. And if I think about what the square root of the potential is, I can see that phi actually has fixed residues. So there'll be some simple pole at the point qi, but it will just have some fixed constant residue. And so phi has fixed residues. And in particular, if I take some vector field W on my space X, and then I just differentiate phi in the direction W, so I differentiate phi with respect to the parameters in my moduli space, this thing here will have no residues as a one form on my surface. And in particular, if I integrate this one form around any cycle, the answers I get will be consistent. So I can actually think of this thing as defining a class in here. And in fact, I now have a map, fiber-wise map from, so it would depend on H bar because the curve depends on H bar, from the fiber of the tangent bundle of X at P to this homology group that's given by W goes to the cohomology class, represented by the meromorphic one form, or maybe a differential of the second kind, this is the classical language, because it's got no residues, represented by phi, differentiated in the direction W. And this cohomology group has a canonical skew form on it. So this is just the intersection form. So I mean, there's various ways to write it, but if I have smooth representatives of cohomology classes on my curve, then probably the simplest way of writing it is just it's this, right? And we have this map from the tangent bundle of X to some system of cohomology groups that are varying as I move around X. And basically, proposition is that if I define omega to be H bar to the minus 2 of this thing, then that will be a CHK form. Is a CHK 2 form. So this thing here, which I said before was equivalent data to a hyperkähler metric, I claim that in this case should actually be interpreted as the pullback of some intersection form on a family of curves defined by the potential. And so in the last 10 or so minutes, I don't want to go too much over time because it's lunch. I'll sort of sketch how one might show this fact.
So this is form on what? On tangent space at particular point or on the mid?
So this map mu depends on a point in X and also H bar. And so it'll be the pullback to TPF. Sorry, T. It'll be the pullback to T pH bar of F, where F is my F is my correspondence space like this.
So this hypercable structure one particular tangent space, or
it defines a hypercalometric as you move around X.
So you vary P and H.
Yes, so there'll be some poles. So this thing will turn out to be meromorphic because there'll be some degenerations when this curve, but it is yeah, it's a hypercalometric on X. Okay. So to show this thing, we just want to show that one of the things we need to show is that the isomonodromy, so this Twistor distribution, which preserves the Stokes data, is actually in the kernel of omega. Okay. And so the clue is you kind of look at this equation and you can see it kind of looks like the product rule here, but with the wrong factors. So this is some simple observation. And we should rewrite this equation, not in terms of Q, but in terms of this, basically the square root of the potential. And it is rewritten as follows. So this Jimbo Miwa Ueno equation, if I write it out in terms of this one form, is actually just telling me this one form is some exact thing up to some thing here, which I'll call, I'm calling kappa A. And so we want to show that, if you like, mu is orthogonal to orthogonal to kappa A as a cohomology class. Because this two form, this cohomology intersection form is fiber by fiber on these vector spaces is some non-degenerate thing. So one wouldn't expect necessarily that when you pull it back, you get something which has a kernel, but that's actually what happens. So mu actually has a kernel, and in order to show that L is the kernel, we basically need to show that things which are isomonodromic are orthogonal to things in the image of mu. Okay, so I won't do the calculation because that would probably waste your time, but I will sort of explain how one might do that. So the key thing is that this intersection form, even though this formula here, obviously you have no hope in hell of calculating with it, is that in terms of meromorphic representatives of cohomology classes, there is actually a pretty tractable formula. So suppose I have, say, sigma and tau, which are, so these are meromorphic one forms on sigma pH bar with no residues. So they represent cohomology classes. So I'll just say these are differentials of the second kind. Then we use this formula together with Stokes' theorem. So this is a pretty classical way of writing this intersection form with some algebraic thing. So we can rewrite it as a sum of residues. We can rewrite this as a sum of residues. Now, by d to the minus 1 here, I mean we take any antiderivative of tau in the neighborhood of a given point, which we can do because tau has no residues, right? It's a meromorphic thing with no residues. So there's some meromorphic antiderivative at any point. And in particular, because phi has a finite number of poles and we know exactly where they are, you can actually reduce this thing to some, relatively simple expression just in terms of, well, it's an expression that can be written entirely in terms of finite numbers of terms of Laurent expansions. So it's a very, very concrete thing. And in our case, then, if I pull this back by the map mu, then, sorry, if I take two tangent vectors, the formula will be the following thing. And yeah, as I said, phi has, we know what where the poles of phi are and basically what phi looks like at its poles because of that that Q2 prescribed some Laurent expansion around Qi. And so this is something you can really calculate with. And then there's the question of, well, why is this thing even H bar? Why does this thing only have 3 orders of H bar? So why is this actually an O2 valued thing as opposed to having some expansion in many, many orders of H bar? And it follows from the following. Basically, if I look at phi, I can rewrite this close to the pole at x equals infinity in the following way. And this is in practice how you calculate this 2 form. Is you expand in orders of H bar. Plus OH bar cubed. And you basically just have to trust me that the trailing terms in higher orders of H bar, these vanish to quite high order at the poles of Q0, which is infinity. And therefore, this formula for the residues can only pick up contributions from this term, and this term. And in fact, these two both vanish at infinity. So there'll be no contribution coming from this term paired with this term. And so you only get terms of order 0, H bar to the 1, and H bar to the 2 in formula for omega, which means that actually you can think of this as an O2 valued thing. And then there's the question of, well, I've sort of explained how you might show that the kernel of omega is equal to L. We still need to sort of show that, there is a calculation one can do to show that. And I'm happy for people to ask me about that. Yeah, and that's pretty much all I was going to say. I guess, yeah, I mean, if there's anything I would like to highlight, it's just that this hypercalorimetric has a nice interpretation in terms of the pullback of some family of intersection forms. I think that's a novel and interesting way of looking at these constructions of joy structures from quadratic differentials. And indeed, I didn't show at all that what one gets is a joy structure, because the joy structure is a complex hypercalorimetric with various axioms for all the symmetries it could have. But that will sort of have to wait for another talk. But yeah, thanks very much.
is the part where you put your in algebraic curve.
Yep.
Y square equals Q. Right?
Sure.
But then before you have written some, E.
Oh, yeah. What's the relation? So the ODE is just psi dash dash derivative with respect to x. So this is just the algebraic curve defined by the potential.
Right.